Hello and welcome back to Let's Roll the Intro. So, in this video, we are going to derive the center of mass, the location of the center of mass of a uniform straight rod. Yes, we all know that it is at the geometric center. If this L is the length of the rod, then it will be at its center L by 2. But let us prove it mathematically. First, let us know the definition of center of mass. Suppose these are the coordinate axes. X-axis, Y-axis, Z-axis. These are two particles M1, M2. M1 is the mass of this particle, M2 is the mass of this particle. R1 is the position of this particle. Position of a particle is a vector. We indicate it by this position vector. R1 is the position of this particle. R2 is the position of this particle. Now, where will the center of mass lie? Center of mass is the mathematical definition. It is the weighted average of all the masses of these particles. Its definition is RCOM. That means the position of the center of mass is M1 R1 plus M2 R2 dot means there can be many more masses, M3, M4, M5, like this it can continue, divided by the total mass M. Here in this case it is M1 plus M2. There can be more masses. Acha. So this one is the definition of center of mass. We can limit it to the x-axis. Suppose all the masses are lying on the x-axis, then obviously the center of mass will be on the x-axis. Suppose the mass is lying only in the xy plane, then the center of mass will definitely be in the x-axis. We can say it by common sense. Here is the center of mass, RCM. By common sense, we can say that it will be on the line joining these two particles. Achha. Now let's move on to the derivation of the center of mass of a rod. Suppose this is the origin. A rod is lying like this. This is 0, 0. This is L, 0. So L is the length of the rod. Now you see this width of the rod. We will ignore this. We will consider that the rod is lying only on the x-axis. Its thickness is 0. It only has a length. So its center of mass will lie on the x-axis. So let's start. Now this rod is made up of infinite particles. With every distance you go forward, we will find a particle. For every dx distance you go forward, you will find a particle of mass dm. So what shall be center of mass? dmx1, dmx2, dmx1, x3. We add all this and divide it with this mass of the rod, that is dm plus dm plus dm. Integration dm, that is capital M, the mass of this rod. Now what is dmx1, dmx2, dm3? That is integration of dmx divided by the mass of this rod. This is the xcm, the position of center of mass in the x-axis, because ycm will be 0, because there is no mass of this rod in the y-axis. So obviously we can say that its mass will be lying, center of mass will be in the x-axis, because its mass, total mass is in the x-axis. Now let's start. We move x distance forward and cut a small element of length dx. Its length is dx. Since this is a small element, its mass will also be small, that is dm. Now this rod is a uniform rod. That means its density is uniform. What density? Linear mass density. Length density we can say. Total mass is m divided by total length. It will give us a ratio, that is mass per unit length. Mass per unit length is constant. So we can also write it is equal to small dm by small x. since mass per unit length is equal. So what is dm? From here we can write dm is m by L into dx. Now let's move here. It's integration of m by L x dx. This dm we replace it with this m by L dx. Now where should we write the limit? X is starting from where? From 0. Where it is ending? L. Then m by L. What is integration of x with respect to dx? It's x square by 2. X square by 2. From where to where? 0 to L. So this mass by capital M is always there. Don't forget it. M by L. X square by 2 we can write L square by 2 minus 0, that is L square by 2, divided by M. This M dies. This L dies. Finally we get L by 2. Thus proved that the center of mass of a rod lies at its geometric center, that is at L by 2 from one of its side. Thank you. Let's roll the output.